look more closely and in detail at how our society and humanity transform Earth's metabolism. What defines the characteristics of the Anthropocene? To begin with, I would like to introduce the notion of a tipping point or breaking point, which is called tipping points in English, and is a very important concept for understanding this upcoming notion of a planetary boundary. Complex and dynamic systems have tipping points that are indeed very difficult to anticipate. It is not easy to understand, but by way of analogy, I would like to take water. So imagine that you are immersed in cold water, very cold water, all right? Also, imagine that you are resisting the cold well. So it's 3 degrees, 4 degrees, you're there, you're in the water, it's cold, and then people come and tell you, but you know, it's very troubling because if it drops a little more, an absolute catastrophe will happen. So maybe, but you, for the past 10 degrees, you've been told it's going to be an absolute catastrophe, it's just a little bit colder, you really don't see what the issue is, and then obviously when it's 1 degree, you still don't see what the issue is, and then at 0 degrees, suddenly you see what the issue is. Because when you wake up, you're in the ice and it's a whole different story. All right, so we could take the analogy in the other direction. It would work exactly the same way. At 98 degrees, 99 degrees, everything is fine because the water is hot, but we are in the water. And at 100 degrees, poof, we are in the steam, we are in the air. What happened? There was a transition, in this case a phase transition, and within a very small interval, in this case a temperature interval, we moved to 2 states of matter that are strictly different, that have nothing in common, are not at all the same. Imagine that our society or our species is well adapted to living in water. If we transform it into ice or if we transform it into water vapor, obviously it will not find that very interesting at all. The notion of tipping points is that sometimes you have very subtle, very small differences, which can even be considered trivial, that will cause a shift from one regime to another. And this transition, which is difficult to anticipate, especially if it is not known beforehand, poses considerable risks that are shrouded in uncertainties. These notions of tipping points are not just theoretical. One of the best and most well-characterized examples is that of cod fishing. Since at least the 17th century, European boats have been fishing for cod off the coast of Newfoundland in 4 major fisheries, and over the last 200 years they have brought back an average of around 500,000 tons of cod per year, which is just enormous. Here, it is one of the largest fisheries, and so it is between 200,000 and 300,000 tons of cod per year. There are good years, less good years, but fundamentally nothing changes for 200 years. As you can see, by 1960, boats were equipped with much larger nets, fished much deeper, and developed sonar, etc. As a result, we ended up with an absolutely considerable amount of fish caught. We are talking about approximately 800,000 tons for just 7 fisheries. For all 4 fisheries combined, it's 1.8 million tons if I remember correctly. And this is something that will happen over 1, 2, 3 years, and then practically nothing, a drop to around 150,000 tons. Despite everything, what does the Canadian government do? It declares the Newfoundland area an exclusive economic zone. It excluded the Europeans to keep the right to fish for a few more years. So we have overfishing, a collapse of the stock, and what is more concerning, no recovery afterwards. Even today, cod fishing is still extremely and very strictly limited. It is only on the order of a few tens of thousands of tons per year. The stocks are not able to replenish. There are still no large cod that are actually capable of producing enough offspring to, in fact, replenish the stocks. Indeed. And there are still many unknowns about why it collapsed first so quickly, and second, why it didn't restart immediately afterwards. But all this to say that if we go back to our analogy of a person swimming in very cold water, when we don't know where the tipping point is, when we don't know where the breaking point is, it is extremely difficult to anticipate and know how far we can go. After all, maybe we could have gone there, up there, we don't know. And besides, in the 60s it was said, great, we have found new ways to catch more fish, we are going to make more money and feed more people. So there was no fear that the stocks would collapse. Now that we have seen this once and it has been reproduced in other ecosystems, it is clear that there are limits we cannot exceed, because beyond these limits there is a collapse followed by something unknown, a major uncertainty. This notion of tipping points is completely central in all the literature around the Anthropocene and has been the subject of several papers. I would like to present two diagrams very quickly. The first one is the one that provides the general philosophy of what we are trying to do when we think about limits and tipping points. If we imagine that the Earth, oscillating between glacial and interglacial periods, follows a cycle of this nature over 100,000 years, climate warming in particular, which we will describe soon, takes the planet on a different trajectory, which is not its classic cycle. And so the question is, how far can we go? Can we go this far, this far, this far? Can we try to predict the mechanics of the system? Can we bring it back to its natural oscillating system? Or are we perhaps heading towards a completely unknown trajectory? Possibly. The risk is that once we step out, much like with cod, once we pass the peak, once we leave the known zone, there are so many uncertainties that we can no longer predict the system, and it can be catastrophic. The teams of Volker and Rockström have thoroughly and meticulously studied the major biogeochemical phenomena of the planet and have identified about 15 major systems that are represented here, each of which is likely to encounter tipping points or to shift from one regime to another, following transitions that are uncertain and risky. The specific color code here represents the important temperature at which these tipping points can be triggered. Between 1 and 3 degrees, there is a significant risk of major ice melt in Antarctica and Greenland. Between 3 and 5 degrees, there is a major risk of a rerouting of the jet stream or an alteration of the boreal forest, etc. This color code, these different systems, in a way establish the map of the major risks that must be avoided. And it is from the study of these mechanisms that the notion of planetary boundary was constructed, particularly for climate change. The famous planetary boundary model, first published by Rockström's team in 2009, is an extremely interesting model because it is both very visual, very illustrative, and can help understand what we can and cannot do. On this slide, what we observe is a kind of pie chart with 9 large sections and then 2 circles. So how does it work here? In a pre-industrial era, the Earth system is outlined with the 9 major categories. These are the famous planetary boundaries that come from the Rockström model. Among the most well-known are climate change, the integrity of biodiversity, the biosphere, land use, water use, biogeochemical cycles, specifically nitrogen and phosphorus, ocean acidification, the amount of aerosols in the atmosphere, ozone, which we will discuss in a moment, and what he calls new entities, namely the set of molecules, of which there are now more than 100,000 produced by chemistry and whose consequences we know very little about. That's for the camembert, you know. Now, what exactly is the meaning of the different circles? The first delineates what they call the safe operating space, which truly means the boundaries within which humanity must remain if we want to evolve and navigate within the normal biogeochemical cycles. Beyond that, we enter a zone of significant uncertainty. And then beyond that, we enter a zone of significant risk. So in a way, we have 3 concentric rings. At the center, where we need to be in the middle, where it is not good to stay, and you must return to the center as quickly as possible. And then beyond, what must be antagonized as quickly as possible because the risks are too significant. Now, what we will see in the upcoming slides is the gradual evolution of this model over time and in detail. So here we are in the pre-industrial era. There are no thermal machines yet. The human population is below 1 billion individuals. We are within the planetary boundary. We now arrive in 1950, if you remember. This is the moment of the great acceleration. It's the moment when everything falls into place, and we already start to see a very severe impact on biodiversity. It is estimated that the collapse of biodiversity, meaning the disappearance of species, had already been significantly underway by 1950. We arrive in the 90s, and this time we see that there are, in fact, actually 3 major areas in red. Biodiversity still, the nitrogen and phosphorus flows that are starting to emerge, and then the famous ozone hole, which is here, or which takes up all the space because it was the major concern of the 90s. What is interesting is that with the Montreal Protocol, the interstate negotiations, and the consideration of the phenomenon, very quickly, in just 20 years, the ozone hole will be healed and this threat will disappear. and today it is estimated that ozone is no longer a problem on a global scale. On the other hand, what we see now is that biodiversity is still in the red, the biogeochemical cycles of nitrogen and phosphorus are still in the red, and the climate is starting to exceed the frame of uncertainty. We now know that it is approaching the risk zone, and the same is true for land artificialization. Now, we will look more closely at the link between humanity's metabolism and the different boundaries, with the small diagram we had earlier. Instead of having an organism, this time we have humanity, which draws matter and energy from its environment, generates waste and heat. And what are the consequences of this? If we refer back to Rockström's model, indeed certainly a more recent representation, we have exactly the same pie charts as usual, which you are now quite familiar with, and then I have separated in blue the issues related to a decrease in resources, and in pink or yellow, the issues caused by an accumulation of waste. And we see that we fundamentally have a metabolism problem where we draw too much from certain resources and emit too much of certain wastes. We will now look more closely at the different compartments that are in particular the most dangerous. I would like to add a particular point to Rockström's model that is not present in his model because he focuses solely on the functioning of the biosphere. We are interested in the sustainability of the system and will also look at what resources, particularly access to energy and mineral resources, we need as humanity to function. So we have the resources, the depletion of resources or the reduction of resources that are linked to Rockström's system, plus access to energy and mineral resources, and I will start with that. In fact, in the upcoming sections, I would like to distinguish between two things. The first is physical resources, namely energy and materials, what problems this poses and where we currently stand. And in a second step, I will present to you the resources derived from living organisms known as renewable resources. This very simplistic diagram shows how we use materials and energy in a very clear and detailed manner. Materials come from the earth, they are extracted, then we make objects that we use, such as tools, and emit waste. At each stage of this process, energy is needed for extraction, manufacturing, use, transportation, etc. What I have highlighted in orange here are the externalities of the process, that is, the things that will have a direct impact on the functioning of the atmosphere, namely the greenhouse gases produced by fossil fuels, the various types of pollution that come from waste, noting the dispersion, the entropy that causes things that were concentrated to no longer be so. And then, of course, the accumulation of pollution, artificialization, and reinfection have a direct impact on other species and on ours, as there are all sorts of pollutants that will affect health. Here we are going to delve into a major section, which I think you understand by now, is the central role of energy in the entire process and metabolism of humanity. And to begin with, I would like to provide some orders of magnitude so that we can better grasp these notions and especially to see what the masses involved are. So, an average human consumes around 2,000 calories per day, which is equivalent to 2.3 kilowatts. If there is only one figure to remember, it is this one. If we have a great athlete, a very great athlete, it can be double. We can be roughly around 5 kilowatts, but it won't vary by a factor of 100. We are in that order of magnitude. So, throughout the entire day, we will eat a variety of different foods that will give us energy. We will convert it into heat either because we are thinking or because we are using our muscles. We also use materials that will indeed allow us to repair our tissues and maintain our form. What you need to remember is this order of magnitude of 2.3 kilowatt per day per person. If we now compare it to everyday life, 2.3 kilowatt is roughly equivalent to 2 hours of energy consumed by a vacuum cleaner. If you imagine all the things in the house that run and use energy, you can see that we are dealing with magnitudes that are not the same as human magnitudes. The different energy sources, the various contents represented here, or access to energy, will certainly not have the same efficiency at all. The most efficient by far is oil, such as diesel, gasoline, etc. In fact, fossil fuels are actually the most highly energy-dense carriers and allow for the equivalent of 10 kilowatts in 1 liter, which is equivalent to 4 days of human consumption, to put it that way. If you want to have the same thing with wood, you need 2 kilo, which is already twice as much. If you want to have the same amount of energy, you need 1 th3 of natural gas. And if you always want to have these 10 kilowatts with a wind turbine, you will need to build a wind turbine 8 meters high and run it for an hour with an average wind. And if you want to generate the same 10 kilowatts contained in a liter of gasoline using photovoltaic panels, you will need 50 métaises, which will be illuminated at noon by the sun. So these magnitudes of production will now be compared with the magnitudes of consumption. So here we have a representation of consumption with several orders of magnitude. The kWh, which is 1000 a wash. Just to remember, when we use an M, it means there are 1000 kilos, so it's a million. If we use a G, it means gigawatt hour, which is 1000 million, or about a billion. And if we put a terawatt hour with a T, that's 1000 billion, so it's a very big deal with 12 zeros behind it. All right? If we now look at what we do during the day, the vacuum cleaner, either it has a more powerful vacuum or it runs for a long time, but it's around 2.2 kilowatts. That is to say, it is the power that roughly corresponds to the energy we consume in a day. We are around that figure. The radiator is approximately of the same order of magnitude. So, the microwave oven, the dishwasher, the traditional oven, the DVD player, we can see that each time we are in the range of hundreds of watts or kilowatt hours, even up to tens of kilowatt hours. On the other hand, if we obviously want to move a train that is much larger, requiring much more energy, we are talking about the order of a megawatt hour, which is 1,000 times more. And if we want to produce a lot of energy, for example, with a nuclear power plant unit, then we are talking about the order of gigawatt hours, which is 1,000 times more, meaning that with one unit, we could run 1,000 trains, which is the equivalent of 1,000,000 kilowatt hours, right? So why am I telling you all this? Because if we now refer to the works of Jankovici and compare the amount of available energy and the amount of energy we consume with what humans are capable of producing and doing with their small muscles, we arrive at this type of diagram, which is extracted from his site, where you have the energy consumption in slave equivalent. This is a notion he uses to indicate how many humans it would take to do the work that such an object does for us or such a service. And if we now look at agriculture, everything that is done in residential, building, industry or transportation and divide it by the number of people, the figures they handle are around 400 to 500 fictitious slaves, meaning that the amount of energy consumed by an average European is equivalent to the manual labor provided by 400 to 500 people. Another way to put it is that in this great acceleration we saw at the beginning, there was an increase in population. If you remember, the population has roughly increased by a factor of 6. There are 6 times more humans now than there were 100 years ago. But if we consider energy, it's not a factor of 6, it's a factor of 30. This means that human development requires an enormous amount of energy. The heart of the problem for what will concern us now is that the vast majority of this energy comes from fossil fuels that release greenhouse gases and cause climate disruptions. In fact, today, 80% of the energy consumed in the world comes from gas, oil and coal. And all of this, in 2019, not very long ago, are greenhouse gases. These fossil fuels produce greenhouse gases, and we need to get rid of them as quickly as possible if we want a chance to stabilize the climate. So you see the magnitude of the challenge, which is considerable, because if we now take, if we forget about wood, which is stable and cannot go much further because the number of hectares on Earth is still relatively limited, we see that nuclear and renewable energies, even if they have increased, still represent something quite small. So here I took the example of consumption in France over the last 40 years, which gives an idea of the evolution of the energy mix. We see that in the 70s it was mainly gas, coal and oil, primarily as sources of energy. And then nuclear production became widespread, and today nuclear represents a significant portion of the total energy consumed. But even though it accounts for 70% of electricity, it actually represents around 40% of the total energy mix. Why? Because electricity is a form of energy consumed, but there are many others, and obviously all cars, trucks, boats, planes and others, for example, not to mention industry, run primarily on fossil fuels. So even in a country like France, where electricity is largely decarbonized, there is still a colossal amount of work to be done to eliminate greenhouse gases. This widespread dependence of the world on fossil fuels poses two problems. greenhouse gas emissions that affect the climate and acidify the oceans, as we will see shortly. And then another problem, which is the finiteness of resources. Because it is a dense and inexpensive energy, it is very, very developed. But the resources are indeed finite, and there is an expiration date. We will not be able to use fossil fuels indefinitely. So if we indeed start with peak oil, this is a figure extracted from the first article dedicated to the subject by Campbell and Laherrère in 1998. What we see here are the quantities of oil that are currently extracted from oil fields with a forecast of what will happen in the future. So it turns out that today we are in 2020 and we are not quite there yet for a whole bunch of reasons, and particularly because we found other reserves. But the main merit of this paper is that it explains the problems posed by finite resources. If you have finite resources, there will come a time when you will consume enough, say half, and you will then go through a peak, and afterwards you will necessarily exploit less than before. Or, to put it another way, it will always require more energy to obtain the corresponding energy because it will become more complicated, etc. We will start by consuming the energy that is the easiest to extract, and then it will become increasingly difficult. And this notion is important to understand because it is both a question of resources and an economic issue. The more we seek out a difficult resource, the more expensive it will be, the heavier the infrastructure and investments will be, and the lower the yield will be. This notion of peak oil has stirred debate around oil for decades. Some firmly believe that the peak is a critical factor that will precipitate a short-term collapse, while others argue that there will always be reserves to tap into, allowing for stability for decades to come. My point here is not to advocate for one path over another, but simply to state that the physical phenomenon exists and that it has a whole range of consequences. What is interesting in this figure, taken from a report by the International Energy Agency, a conservative and well-respected organization that has not been known to cry wolf, is that in its latest reports it speaks of a significant decrease in the amount of so-called conventional oil due to the need to find new fields to compensate for the corresponding demand, and that unconventional gas and oil will be called upon to the rescue if we want to maintain this plateau. Indeed, today, even the International Energy Agency discusses an undulating plateau, meaning we have reached a peak, a level of resource depletion that will persist over time, not necessarily increasing further and possibly taking time to decline. But this notion of a plateau, in my opinion, signifies that the most pessimistic and the most optimistic are finding common ground on the fact that we are currently not at a peak, but at the top of a bump that may last a little longer, but not indefinitely. So anyway, we need to find a solution because we won't have the means to finance or operate the economies in the coming years. And the other reason, of course, is climate change. I chose this diagram from Carbon Brief because I find it particularly enlightening. It is a little bit complicated to understand, but if I take a minute actually, you have here represented the number of years we have ahead of us before reaching a certain threshold. Here, for example, if we wanted to stabilize the climate at 3 degrees above the pre-industrial period, 3 degrees means that if we want to have a 66% chance of stabilizing the climate at 3 degrees, we would have 55 years ahead of us. Now, we can take more risks and accept that we have a significant risk with only a 33% chance of stabilizing the climate at 3 degrees. At that moment, we have 77 years ahead of us. Years ahead of us, what does that mean? It means years during which we are capable of emitting the same amount of greenhouse gases as before. This is what is called the carbon budget, which is the amount of emissions we produce. So that is 3 degrees. It turns out that scientists have told us that the threshold we must not exceed is 2 degrees. Beyond that, we are at a tipping point, we are in uncertainty, and the risks are considerable. So 2 degrees drastically reduces this window of opportunity, because if we want to have a chance to stabilize the climate, this time it's more than 20 years. All right? So we can take a few more risks, and we'll have about 30 years, etc. And then recent studies show that we have probably underestimated the risks due to climate change, and the threshold currently considered is no longer 2 degrees but 1.5 degrees. And this difference shortens the window of opportunity. That is, the number of years we have ahead of us to continue emitting greenhouse gases without entering into dynamics that will escape our control and lead us into extremely dangerous territories. So 1.5 degrees translates to 5 years on this chart if we really want to have all the chances. So that's 2025. 33 means 16 years, which corresponds to 2035, 2036 if we accept taking a significant risk. These figures are not set in stone. They come from statistical calculations. There is no fateful date that announces the end of the planet. We are absolutely not in that logic. It is simply a statistical explanation that presents the risks incurred based on the amount of greenhouse gases we will emit. What we can see clearly from this graph is that the longer we wait, the hotter it will get, and the greater the risk of something serious happening. Now, let's take a look at the good news. It turns out that this year the COVID crisis has paralyzed the economy and that it leads to a significant reduction in greenhouse gases. We will know more by the end of the year when all the calculations have been done, but from one country to another it ranges between 5 to 10%, which is still relatively significant. But above all, it is a year of transition because we have several pieces of information coming from different parts of the planet, indicating that awareness will materialize into political actions to reduce greenhouse gases. For example, China has indeed announced that it wants to be neutral by 2060. The European Union has declared that it wants to embark on a Green Deal for Europe, and Joe Biden has announced that he wants to implement a Green New Deal to replace fossil fuels with renewable energy. So we are in a global logic of ecological transition, energy transition, and these are words we use a lot. So what does it mean and what is behind it? Today there aren't 1,001 ways to produce energy in a decarbonized manner. Here there are 5. We could use a few more. There are what are called renewable energies. This is essentially solar and wind from a mass perspective. We will see that in a moment. Geothermal energy, which is important in a number of locations, typically Iceland, but which requires specific sites. And then there are the dams, which have historically been a major source of renewable energy, but their sites are nearing saturation because there aren't that many mountains or rivers where dams can be built. And then there is nuclear energy, which is a low-carbon energy source but poses a whole host of problems, particularly in terms of social acceptability and construction time. So, just to give you an idea of the scale, if we look at the same figure as before, where we had our 80% of greenhouse gases, we now see that decarbonized energies, that is the clean energies that we will now need to implement on a large scale, ultimately don't represent much. Today, this is what it represents. So, out of the 170,000 TWn consumed in the world today, all decarbonized energies represent, in the end, only 7,000 TWn. Which is really infinitesimal, at least for now, not at all up to the challenge. So the largest part, as I mentioned earlier, indeed comes from the dams. It is a source of hydraulic energy. Dams produce around 4,000 TWs. And then, over the last 20 years, we have seen an increase in wind, solar, and other renewables to a lesser extent. So, renewable energies are taking off, but they are not yet at the right orders of magnitude, and there are a number of reasons for this. So the limitations of renewable energies, particularly now I will focus on solar and wind, are that they are what we call intermittent. What does intermittent mean? It means that typically you don't have solar power at night and you don't have wind power when there is no wind. And if we look here at Germany's energy consumption over the course of a week, in this case it was, for instance, a few months ago in 2020. It is an autumn week with slightly less sunlight and where the gentle wind may stop. You see that during the first few days there is a very significant consumption of coal, anthracite and lignite to run the steam engines to produce electricity because there is not enough wind, there is not enough sun, and from the moment the wind and the sun arrive, at that point renewable energies produce, which largely allows the erasure of fossil fuels. But here we have a clear illustration of the fact that this is a system that cannot be sufficient today, cannot sustain itself. And just because we have a lot of installed capacity doesn't necessarily mean we have the ability to cover all consumption. Even in Germany, which has invested significantly since they decided in 2011 to phase out nuclear power, these intermittent energies, One way to address the issue is to store the energy that is produced when there is sun or wind and then release it when there is none. This storage capacity, which is currently mainly provided by dams, is expected to develop significantly, either through thermal storage, batteries, or even compressed air devices. But today we can clearly see that these devices are really ultra-minority compared to the overall storage capacity, and the global storage needs are going to explode in the coming years. We are going to need more and more storage capacity to be able to accumulate the energy that is produced, in this case electricity, which is produced by solar and wind when the installations are running, to then meet the needs when it is completely calm or when clouds pass. And there is another problem with these two energies, which is that both require very large infrastructures. If you remember the small diagram, to produce the same amount of energy contained in a liter of gasoline, you need large solar panels or an 8-meter-high wind turbine. What is indeed true for 1 liter of gasoline is even more true for the millions of liters of gasoline consumed today. One of the consequences of this is that if we want to scale up renewable energies, a tremendous amount of materials will be needed. So, this is a paper published by Olivier Vidal a few years ago, which shows that if we want to achieve an all-renewable project on the scale of Europe, for example, we would need to increase the amount of iron by 50 times, copper by 50 times, glass by 50 times, cement by 15 times, aluminum by 90 times, meaning orders of magnitude that are still very significant, because wind power, like renewables, but even more so storage systems and the entire electrical setup that goes with it, will require enormous amounts of materials. However, these materials are also finite resources. And that's why, in a certain way, there is no clean energy or dirty energy. In fact, there is no green energy and actually no brown energy. There are essentially shades of green. And you have energies that have advantages and others that have disadvantages. But no energy access system is in itself capable of meeting all needs and is virtuous in itself. A very good way to go further is to watch the YouTube channel of Le Réveilleur, which dedicates many episodes to the different types of energy access and the carbon balance, allowing you to delve much deeper. To summarize, we are facing two problems simultaneously, and they are interacting with each other. On one hand, it takes more energy to extract and refine metals, and on the other hand, we need more metals to produce energy that is less accessible. So, we have entered a logic where, to ensure energy production, if we rely solely on renewables, we will need to spend a significant amount of energy to extract the metals we need, transform them, etc., which themselves require a lot of energy. We are in a system that is quite complicated to model, and now we will delve further into what this means in terms of metals,